All right, so let's continue our journey in regression analysis. We are going to go from simple regression model to multiple regression model estimation. We call it MRM. This is going to be chapter 3 of the Wooldridge textbook, and it's going to be a lengthy one. We're going to spend 4 sessions or a couple of weeks on this chapter, and then later on, through the entire rest of the semester, we will expand the ideas of multiple regression model. Okay, so let's begin with the motivation. Why do we need to go from simple regression model that only controls for one exponential variable to a multiple regression model that obviously we can control for many other exponential variables? So in terms of motivations, number one, the multiple regression model incorporate more explanatory variables, more controlling variables or controlling factors into the model. Remember, our original example, use a blue one. We said that, let's say we want to see what's the relationship, what are the factors that are affecting the wage, right? At the beginning of the semester, we explored some idea. We said maybe education, maybe experience, maybe gender, also, for instance, tenure, and let's say talent, and etc. Right. In chapter 2, we said, okay, let's ignore all of them and let's just pick one of them. It can be education, experience, any of them, right? And in simple regression model, we picked only one of them. So for instance, we picked education and we called everything else unobserved variables, right? Those unobserved factors, we call them error or disturbance term. And we said that, maybe we put them in the unobserved factors because for some of them, we really had information like experience, gender, tenure. But for some reason, for some technical reason, we were not interested in putting them in the model, right? For some other variables like talent, we literally had no information. So we had no other choices but to call it unobserved factor, right? And so this is a simple regression model. However, now we're going to move to multiple regression model. We're going to say that, okay, I'm going to control for wage. When I want to predict wage, I want to control for education, experience, gender, tenure, and let's say, I don't know, I don't have information on talent, or maybe lots of other exponential variables out there. I want to call them unobserved factor, right? So again, for multiple regression model, we are going to say that, okay, let's regress wage on education, on experience, on gender, and etc. And at the end of the day, there's still going to be maybe lots of other exponential variables out there that we are unable to control for them, right? Because to be realistic, we cannot control for thousands of variables, right? In regression analysis. In machine learning, we can, but in regression analysis, because we want to interpret that, we need to work with large data sets and things like that. So in econometrics, we're going to say that, okay, at some point, we have to stop controlling for all the exponential variables out there, but still, maybe controlling for 10 of them, maybe controlling for 20 of them. It's going to be a good idea, right? So number one, multiple regression model is going to incorporate more controlling factors. So that's important. Number two, with controlling for those other explanatory variables, we can explicitly hold them fixed. This is very important, okay? Because remember, in simple regression model, we said that in order to have a causal interpretation, the notion of ceteris paribus was playing an important role, right? We said that we have to be able to hold everything else constant. Then let's say that what is the pure effect of, let's say, education and wage. So in simple regression model, we just assume that, implicitly. In multiple regression model, however, we can explicitly assume that. I can say, I can hold experience, gender, tenure, and etc. Everything else constant explicitly, and then see what is the pure effect of education on wage. So that's the power, that's the beauty of multiple regression analysis. Because guys, remember, in econ, finance, marketing, you name it, usually the data sets that you're dealing with are observational data sets. It means that it's not, experimental data. We haven't collected the information in the lab. We cannot specifically hold them fixed, right, for the observational data. However, multiple regression analysis is going to enable us to holding everything else constant, even for the observationary data. So this is a big deal. We're going to talk about this a lot more when we get to the intuition of the multiple regression model. So that's motivation number 2. Number 3, this is also very important. It allows for more flexible functional form, right? Because let me give you an example. Imagine I was regressing only wage and education, right? I say that, okay, wage is equal beta 0 plus beta 1 education plus, let's say, u. I couldn't put any other explanatory variable in the model, right? Either quadratic or to the power of 3, to the power of 4. I was not able to do that because in simple regression model, we have to only include one variable. However, in multiple regression model, we can come up with more flexible functional forms. So I'm going to say that maybe wage is a function of education, and for some reason, we're going to talk about the reasoning behind these things, but let's say maybe it's also a function of education to the power of 2 as well. So because I can have 2 explanatory variables with multiple regression model, I know I'm able to do something like this, and then maybe a bunch of other variables, and then u. So this will enable us to literally, instead of fitting a simple line, we can fit a curve to our data set. So this is very powerful. So remember, last time we talked about this thing. Imagine education, wage versus education is like this. We said one way to deal with this is to transform this data set to a log level data set and make it like this by doing a log transformation and then do a fitted regression line. However, so this was our friend log wage versus education. We're going to say that, you know what, do not use log transformation. If you have multiple regression model, so let's say wage and education, and you believe that the relationship between wage and education is like this, then you can put education square into the model. If I put education square into the model, then we're going to have a fitted curve instead of fitted line. So that's very powerful, right? Again, which one is going to do a better job? We don't know ex ante. We are going to use data and see, at the end of the day, which model has a better adjusted R-square. So this is how we are going to deal with that, right? But for now, what is important is that, with multiple regression model, we are able to do analysis like this, which is very, very powerful. Okay. Now, let's look at a bunch of examples from the textbook and go over the interpretation, how we interpret the coefficient in multiple regression model, and etc. So let's say we're going to stick to our model wage versus education and experience. Here we are regressing wage on education and experience. So what do we have? Wage is equal to beta 0 plus beta 1 education, beta 2 experience, and plus u. Again, I can go on and put lots of other explanatory variable in the model, but let's, for the sake of argument, let's say we stop here. We only add 2 explanatory variable in the model and then call everything else unobserved factors, right, or error term. And let's say the units of wage is hourly wage, and education is years of education, and experience is years of labor market experience. So what do we expect to see? So the coefficient of education most probably is positive, the coefficient of experience is positive, but we're going to use data, and then, so at the end of the day, I'm going to use y, and now I have multiple x's, x1, x2, and etc. Right? In this example, x1 is education, x2 is experience, and then I pass this data to OLS, and OLS is going to give me back beta hat 0, beta hat 1, and now we have beta hat 2 as well, right? We're going to see that we are going to have k of these beta hats down the road, okay? So the process is exactly the same as simple regression model, so that's why chapter 2 was such an important chapter, because if you have a good understanding for simple regression model, we can easily expand it to multiple regression model. All right, so let's clear some terminology. Again, everything is going to be very much the same as simple regression model. So for instance, we're going to say that, multiple linear regression model explain variable y in terms of variables x1, x2, and up to xk. Okay. So one important thing is that I want you to distinguish between these x1, x2, as different, as separate variables, not different observations, right? So when it comes to the notation, sometimes the students are confused because in simple regression model, so for instance, I had y, x, you remember we said maybe I have observation number I, so we said y1, y2, and etc. It was x1, x2, etc. So this is one variable. It can be education, and x1 was education for observation number 1, x2 was education for observation number 2, and etc. However, in multiple, so this was simple regression model. In multiple regression model, we have a y, we have x1, we have x2, we have x3, and etc. Right? How do I distinguish x1 for different observations? So I'm going to say, for instance, y1, and then I say x11, x12. Yeah, oops, sorry. x12, the y2, x13, and etc. So for instance, this is x21, x31, x22, x32. I hope you get the idea. x23 and x33. Okay? So don't get confused in terms of terminology. So they just clear it out. What are these subscripts used for? Okay? So in general, we show it with x, I, j, and I stands for the variable index. J stands for observation number. Observation number. Okay. And our general model is like this. Y is equal beta 0 plus beta 1 x1 plus beta 2 x2 and beta 3 x3, etc. up until beta k xk plus u. So how many explanatory variable I have from 1 to k? So we're going to have k explanatory variables. So this is a general multiple regression model. In simple regression model, what is k? K is equal to 1 because we have only one explanatory variable. In multiple regression model, k can be 2, 3, 4, and etc. Right? Everything else is the same. Y is our friend dependent variable, explained variable, response variable. These are different names. And what else we have? X1, X2, X3 up to xk. These are independent variables, or we call it explanatory variables, regressors. And things like this. And finally, the U is error term, disturbance, unobserved factors, and etc. Right? And betas, beta 1, beta 2, beta 0, we call it intercept. Beta 1, we still call it slope. But guys, these are not good terminology, at least good words. I don't like them. I think Wooldridge himself mentioned it in the textbook that he doesn't like it either. But because it's part of a convention that we call them slope, we're going to continue calling them slope because you're going to see that we're not dealing with a line anymore because we are not in two-dimensional space anymore. If it is y, x, this is not the data, and we don't have something like this. So if you call it a slope, that's kind of not quite right. If you go beyond 2 dimensions, so let's say we go to 3 dimensions. Actually, I'm going to show you a nice presentation of regression analysis. Then we're going to deal with a fitted plane instead of line, and then beta 1 beta 2 doesn't mean slope anymore. Imagine go to even beyond 3 dimensions, go to 4 dimensions, 5 dimensions. Then we have human eye has no idea what are those shapes or objects, right? So calling them slope is not necessarily quite right. But again, for the sake of argument, let's just call them slope parameters. Okay. All right. What about interpretation? This is very much the same as simple regression model. Do you remember in simple regression model we said something like this? Beta 1 was equal to delta y divided by delta x. And we said if x increased by 1 unit, then y is going to increase or decrease by beta 1 unit, holding everything else constant. Do you remember this argument? If delta u given delta x was equal to 0, or basically if we explicitly assume that everything else is constant. Okay. In multiple regression model, we can write this equation for every single beta, for every single x, right? I have x1 to xk. So I'm going to replace this beta 1 by beta j, and it's going to be something like this. What is j? J is a number of explanatory variable. Okay. So for instance, beta 1, beta 2, beta 3, beta 4, and etc. up to beta k. How we interpret them? So the interpretation is again as simple as a simple regression model. However, there's a slight difference between the two. We're going to say that by how much your y variable changes, right? Does the dependent variable change if the jth independent variable increase by 1 unit, right? Then here, however, we're going to holding all other independent variables constant explicitly, and we also assume that all the error terms are constant. So the big difference between simple regression model interpretation and multiple regression model interpretation is that now we can explicitly hold everything else, all the other explanatory variables that are in the model, fixed and constant. This is very powerful. So the multiple regression model manages to hold the values of other explanatory variables that are in the model fixed, even if in reality they are correlated with the explanatory variable under consideration. So let me give you an example. Back to our simple example, wage versus education, right? Beta 0 plus beta 1, education plus beta 2. Let me actually make an example. Beta 2, gender plus U. Okay. All right. So imagine, we have no idea what is multiple regression model, right? So imagine this was the model, simple regression model. This thing is plus a U. How did you interpret that? We said, okay, if education increased by 1 unit, holding everything else constant, then wage is going to increase or decrease by beta 1 unit, right? We assume that we are holding everything else constant. So basically we know that in the data there are some male and female, right? We assume that we are looking at the data. Again, this is some assumption that we look at only the females and read the effect of education on wage, and then separately we look at males and saw the effect of education on wage. But that was implicit assumption. However, in multiple regression analysis, we can literally control for that. We can literally fix the gender. So this means that I can go ahead and filter the data. No, this is wage, education, gender, right? So some of them are female and some of them are male. And I want to see what is the pure effect of, let's say, education on wage, and I fix this variable, female. So basically, the OLS is going to use only this part of the data set and calculate the beta head 1 for you from this part of the data set, and then report that number for you. And again, it's going to simultaneously do that, holding everything explicit. So this explicit is coming from here. We can literally, so that's the idea. We can literally hold other explanatory variables fixed. And this is our ceteris paribus interpretation, right? Because we said that without ceteris paribus interpretation, we cannot say anything about the causality in the model. So that's the power of multiple regression model. Even, again, I repeat myself, even though we are dealing with observational data, which means that it's not a data that we collect in the laboratory, right? Even though we're dealing with observational data, multiple regression analysis enables us to have a ceteris paribus interpretation. And the more factors that I'm controlling for, the more confident we are that this is not pure correlation. This should be something more than correlation, if it turns out to be significant at the end of the day. Okay, finally, it has still to be assumed that unobserved factors do not change if explanatory variables are changed. So look at that. So for instance, in this example, we said, okay, we are controlling for education and gender. However, we are still calling everything else constant, everything else as unobserved factor. And we are explicitly assume that everything else is constant, okay? Or implicitly, sorry. So we are making that assumption implicitly. All right, so yeah, that's pretty much it. Now let's look at a bunch of examples from the textbook. And I'll finish this video with, I think, going over a couple of examples, and then we do the second half in another video. All right, let's say we want to predict the college GPA by looking at two variables, high school GPA and ACT score. And again, you can give this and give it a try and see if these numbers make sense for you. So you have your high school GPA, plug it here. You have your ACT score, plug it here. Use these numbers, do the multiplication, add 1.29, and see if this is close to your college GPA or not. Again, this is a model, right? We don't know if it is right or wrong, but at least you can give it a try based on the data set that we are using in the textbook. These are the real numbers. Okay, real data set, real number. So this is, and there's a good chance that for you these numbers doesn't make any sense. We're going to talk about them later on, but let's focus on the model. So again, college GPA is grade point average at college. High school GPA is high school grade point average. So these are the averages, point averages. And ACT is our achievement test score. How do we interpret? Again, all we care, not all, the main thing that we care in regression analysis is how to interpret things, right? Calculation is easy if you're going to do it in R. So let's say, we're going to say that, let's first interpret this number. How can I interpret that? So we say if high school GPA increases by 1 unit, right? So far, so good. If high school GPA increases by 1 unit, now this is new. And we are holding ACT fixed. We are explicitly holding ACT fixed. Then, on average, the college GPA is going to be 0.453 or 0.45 points higher. Does that make sense? So this is how we interpret that. Well, let's do it like this. Holding ACT fixed, another point on high school GPA is associated with another 0.453 points college GPA. Okay, so this is one way to do that. Another way to interpret this exactly same number is, let's do it this way. If we compare two students with the same ACT, again, I want you to realize where is the power of multiple regression model. We can explicitly assume that we're we are fixing ACT fixed in this example, right? So we say it like this: if we compare two students with the same ACT, in your data set, if your data set is large enough, there's going to be a good chance that many people have exact same ACT. So you can compare two of them, right? So if we compare two students with same ACT, but the high school GPA of a student A is 1 point higher than the high school GPA of a student B, then the college GPA of a student A is going to be 0.453 higher than the student of B. Does that make sense? So these are exactly the same. If you write any of them, well, that's a correct answer. So this is the right way to interpret them. Okay. And now let's interpret this one, 0.0094. Because it is 0094, well, I can say holding high school GPA fixed, 1 unit increase in ACT will lead to 0.0094 unit increase in college GPA. Or again, in order to make make more sense, we're going to multiply it by 10 and say that, okay, holding high school GPA fixed, another 10 points on ACT, 10 points on ACT is associated with less than 1 point in college GPA. So where is this coming from? If I multiply 10 by this number, so I get 0.094, so it's roughly 1 point. Okay. Well, less than 1 point in college GPA. All right, let's quickly look at another example. Imagine we are regressing average score on expenditure and average income. Okay, what are these things? So average score is average standardized test score of a school, and expenditure is per student spending at this school, and average income is average family income of students at this school. So again, this makes perfect sense. Imagine you want to see what is the effect of average family income and not university, the school expenditure per students on their average on your score, right? So what do you think in terms of the sign of beta 1, beta 2? Most probably both of them are positive. But what's the idea of this example? We're going to say that there's a good chance that per student spending is correlated with average family income, right? Because again, the wealthier the families are, maybe the more contribution they have to the school, and then the more dollar available for per students to expand, right? So there's a good chance they're correlated with each other. If that's the case, then they're going to say that, if you, for some reason, okay, for some reason, if you drop any of them, either average income or expenditure, it really doesn't matter which one, but imagine you drop one of them. So let's say here, for example, if you drop average income, in other words, if you use simple regression model instead of multiple regression model, what will happen? The thing, most probably what you're going to see that the coefficient of our expenditure, beta 1, which the model is going to calculate without average income, it's going to be biased. So we call it, that's a biased estimate, because it is, it is not the pure effect of expenditure on average score anymore. We know that it's a combination of effect of expenditure and average income on average score. But in simple regression model, we are simply ignoring this variable. So that's why we're going to say that beta hat 1 is going to be biased. Next class, we are going to quantify this bias. We call it omitted variable bias. But for now, I want you to understand the intuition. So what's the problem with simple regression models? So far we haven't talked about it. So the problem with simple regression models is that if you're dropping any of these things, expenditure, average income, there's a good chance that the coefficient that the model calculates at the end of the day is going to be biased, because that's not the pure effect of expenditure on average score. Okay, and multiple regression model, by the way, fix it by including this variable into the model. Okay, so we already covered these two. What is the third one? So in a simple regression model, the effect per student spending would partially include the effect of family income on the test score. So it's not purely effective expenditure on the test score. And again, this is one of the other advantages of multiple regression model. We are going to quantify this number later on. All right, so let's pause the video here actually, and in the next video I'm going to talk about a couple of other examples from the textbook that we are going to incorporate these squared version of the variables in the model. We're going to see how we should interpret the coefficients now, because interpretation is slightly tricky and different. All right, so let's stop this one and see you in the next one.